we will continue on with applications of mechanics, and more specifically, part B, and that's the application of motion, and even more specific, projectile motion that we'll talk about. To do that, though, we needed to not just solve for parts of a vector, okay, but now we're going to require a certain set of equations. Okay? So there's going to be a certain set of equations. Technically, all of them can be derived, algebraically substituted from the equations in which you already have. However, I find it easier for students to say, here are the equations that you will need, instead of going through and algebraically manipulating everything for them. So here are the equations. The first equation is a manipulation of the acceleration equation. This equation is just an algebraic manipulation of our original acceleration equation. I think when you look at it, it makes like, oh, I see. It gets rid of that negative VI, which bothers sometimes people. Okay? After that, we start to have more algebraic substitutions. These three are equations that you will want to have. This equation is very similar to that of the distance is equal to 1/2 gt squared. What has been removed of it was the initial velocity. And so that's why we have this now. Now, where A can still be gravity in some cases. And we have to be very careful. We have to read questions carefully. And again, when in doubt, drawing it out. If any time something is projected through the air, or falling off a table, or falling off a cliff, gravity is going to come into play. Because it's going to fall. And therefore, if it can fall, the acceleration can be substituted that A can equal gravity. It doesn't always equal gravity. It can sometimes. This equation is sometimes useful, especially when you're not given an acceleration. Usually only used horizontally. Okay? Usually just with horizontal objects. There are two that we use a lot. Those two we use the most. They become the two equations that we use the most. So making sure we know them. Making sure that we have them written down somewhere will be very important. So let's try it out. We'll not do full projectile motion problems yet. We'll deal with things moving in one dimension first. A car starts from rest and speeds up. and acceleration of 3.5 meters per second squared. After the traffic light turns green, green means go. How far will it have gone when it's going 25 meters per second? So there's a lot going on here. So we got a car, and we can, again, when in doubt, draw it out, right? So let's draw it out. Rudimentary car here, well, some gray tires. Okay, little windshield on there. Side windshield here. Yeah. A little small back seat. Okay. Big front end, big engine, right? Set the light stop. Right? Traffic light, little thing here, right? It's old school one, so it's on a post. Right? Traffic light goes green. Okay. What is the initial velocity of that vehicle as it sits there? 0. Believe it or not, very important to note that the initial velocity is 0. Okay, so there we go. V sub I, 0. 0 what? Meters per second. All right. It's going to accelerate at 3.5 meters per second squared. We want to know, and we'll get a different color green here. Distance in the x direction when the v sub I f equals 25 meters per second squared. No, meters per second, not meters per second squared. There. That's what we're looking for. The thing that we don't have, a lot of people will want, and that's time. I don't know what the time is. And we do have equations that can solve for things if we don't have time. I find the equation to use, and that is v sub f squared is equal to v sub I squared plus 2a technically change in displacement. Gonna resize this. And now all I have to do is plug what I need to know in, or what I have in. I have my v sub f squared is equal to 0 squared plus 2 times 3.5 times change in distance. 0 squared is easy. 3.5 times 2, 7 times delta D equals 25 squared 625. I need to divide both sides by 7. To give me my answer of 89.3 meters. So a problem like this can be a little bit tricky. So we'll we'll have our our road here, and then we'll look at maybe doing a little car initial part. Okay, draw it in a little bit more of a one of those station wagon kind of van things maybe going on here. Tinted back windows, passenger window there. And now what it is it has to brake. Maybe it saw a cat, a squirrel, I don't know. Most people speed up for those types of things. Some people avoid those things, to each their own. So it needs to stop at that point. And so I'm going to draw my hypothetical car, kind of be more in that grayish tone with it. And so we have that same idea of, okay, that's where the car stops. And I think this is when we have to be looking at some things, and drawing things out does help, in that it is initially going to be going, so the initial velocity is going to be 25 meters per second. The final velocity is actually going to be 0 meters per second. The time interval, and I write this in black because it's a scalar quantity. The time, and this is kind of your reaction time between when you should stop and when it takes your brain to go, oh, I got to stop and press the pedal. There's going to be a time delay. No matter how good you are, there's a time delay. And so there is going to be that. And so we then also have a deceleration. In all reality, that slows down at a steady rate, because it's slowing down, should be at a negative 8.5 meters per second squared. We are asked to find that distance that it takes for it to stop. Now this is again where we have more than one equation that technically could be used to solve. However, we have to make sure we're using the right one based on the science that we're looking at. And so if we look at the science part of it, and looking at the fact that we have to account for the distance traveled during the time that they go, oh, I should brake. You're still driving down the highway. You don't just magically pause and then move on. You have to take that into account. And so in a way, taking that into account utilizes the equation of distance is equal to the initial velocity times time. And in all reality, that's that initial moment in time, that moment in time that you're like, oh, I should stop. That reaction time, it's taking that into account right there with that. And so then you say, okay, that's what it's doing, how much that distance that it takes, and then you add in the 1/2 AT dt squared in on top of that. So now you have, instead of, essentially why we can do something like that is you are taking that into account with those two different things. And so I'm going to resize this now that we kind of have some things established so we can kind of show our work here. And what we have is we have our initial velocity, and so I'm going to substitute items in and say that my distance is equal to my initial velocity of 25 meters per second times my time of 0.4 seconds plus 1/2 a, which is technically a negative 8.5 meters per second squared times time squared. It's not very good 2 there. Which the time again is 0.4 seconds. So I'm going to do some of the calculations, and I'm going to do kind of some of the calculations in bulk in 2 steps. And so I'm going to multiply my 25 times 0.4 to give me 10. And in all reality, this would be meters per second squared on it, but we'll just kind of keep the labels off of it as it might confuse some people with that. Plus, now I'm going to square my 0.4, making it 0.16, and then multiplying that by my 8.5, the acceleration, and then multiplying that by 1/2, or 0.5, to give and this is technically a negative 0.68. So what has happened now is I will take 10 and subtract the other to give me 9, distance, I'm sorry, of, wait a second, that doesn't look right. It should actually be, greater of the 2. Maybe that's where it is. I think maybe we go that route, and then we add that together, because that does not make sense that it would be shortened distance than it would have traveled otherwise. So then it would be 10.68 meters to come to a stop. What I believe would help us out if we evaluate our answers to make sure that those answers are taken into account as the part of the fact that it is slowing down. It is there, but it is, I think, also still going far, even if it is accelerating at a very large rate. The distance that it travels can't be less than the distance traveled in the reaction time, is why led me to that miscue of going, oh, maybe I miswrote the acceleration as that as a negative instead of it should have been a positive. So kind of evaluating our answers is an important skill to do.